Okay, so I'm recording this session for those na hindi makakasama today, no? Um, so today, and let me just look at the oble, no? Check lang natin yung oble. We are dapat by now nasa module 4 na kayo. So module 4 is all about plastic deformation and dislocations, no? So if you look at the course guide, let me just view the course guide, no? So, nasaan tayo? We are at this point, no? Nandito tayo. March 15. Wait lang, ah. Okay. So, hopefully na tapos nyo na yung mga modules na to, no? Especially for solidification, that is na covered na natin yung elements of grain boundaries pati yung nucleation and growth, and there are several recordings doon sa Google Chat natin, no, that covers the other topics such as diffusion tsaka yung strengthening mechanism, this one right here. So we were good on that end. Ang i-discuss na lang natin is dislocation and plastic deformation. So, doon sa video natin, meron tayong doon sa, if you look at the course guide nun nandito, I'm sorry, if you look at Uble, under dislocation plastic deformation, merong recorded lecture about yung ano no, yung projections and slip systems. Tapos this is actually all about ano no, stereographic projections. So you can just view this on your own. So most of the topics na discuss na sa ano no, MetE176, I think. Tama, nag-stereographic projections kayo sa MetE16. Tama ba 'yon, Lawrence? Tapos na kayo mag MetE16, di ba?
Hello, sir. Hello.
Hello?
Yes po, sir. Tapos na po.
Tapos na-cover naman ni, tama ba sila, Sir Franco at Ma'am Hana at Totoy? Na-cover naman nila yung ano no, yung stereographic projection.
Choreographic. Yes, sir.
Okay. So that's good. Yung dito at least since may ano na kayo, may idea na kayo on stereographic projections, mas mabilis nyo nang ma-apply siya in terms of physical metallurgy, no? And in physical metallurgy, mostly ina-apply natin siya sa crystallography. Okay? So i-cover na lang natin ngayon. We have dislocations, which is I think this handouts right here is self-sufficient naman, no? It has all the information you need, and probably I can add more readings, no? So where we got this information from, so pwedeng kahit excerpts na lang from those books na kung saan namin kinuha to, pwede ko idagdag probably. Tapos ang i-discuss lang natin ngayon is yung meron tayong ano no, kumbaga mga equations involved and problem solving involved. So that will be the hardening part of plastic deformation. Okay? So let's recall some of the terms na discussed na, no? And this is from MetE11. And we have two terms, yung tinatawag natin na true values, and we have the engineering values. Okay, so sometimes iba-iba yung notation na ginagamit, no? Minsan in some textbooks, when you use the Greek term or the Greek the Greek letters, we usually mean true stress sila. Tapos when we use the, ano ba yung tawag sa, nakalimutan ko nung basta ito yung regular alphabet natin, pagka yun yung ginamit natin, then we mean the engineering stress. Okay? So usually sinusulat siya ng ganito na E. Tapos ito pwede rin isulat as E epsilon ln 1 plus E. Okay? So ito, these two equations right here, they just describe the relationship between the true stress and true strain. So and siguro I can just, I don't know, refresh your memories on why we have these two values, no? Kung bakit pa differentiate pa natin yung si true stress versus si engineering stress. Okay? So we recall that stress is sigma, and either sigma, pwede ring S. And in our in the textbooks that we use, usually pag walang subscript, kung yung isa is naka-subscript underscore T, yung isa usually walang subscript, no, that means na engineering siya. Sometimes may mga textbooks din na that has sigma T equals sigma and nilalagyan nila ng subscript na sigma E. This means that engineering sila. Okay? So pwedeng ganyan. So to prevent confusion, no, we will just use ito. So ilalagay na lang namin anytime that we are referring to engineering stress or engineering strains, we just use the subscript na E, no? Tapos pag true, we place a subscript T. Okay? So just to make things clear. But just note na in some textbooks, hindi na nila nilalagay na yun, no? And baka when you're researching on your own and you find some of the terms na parang unfamiliar sa inyo, at least may idea kayo kung paano siya sinestate. This also ito, no, itong sigma and S, also a very common convention dito. Something that some references also like to use. Okay? So again, pagka meron tayong stress value, and let me just write stress na lang, no, para mas malinaw. Yung stress is usually written as a force over an area. Okay, so that's what we call stress, and sometimes we call this as pressure, no? So it's the amount of force that is applied on a given area. So whether that area is perpendicular area or a parallel area, no? So if it's a perpendicular area, then we call that as a normal stress. Okay, normal stress, sometimes tensile stress, depending on the direction, o pwede din siyang compressive stress, pwede din siyang tensile stress. Pero in general, we call them as normal stresses. No? So this is when we have something, this is the area, kunwari, and we are applying the stress either this direction or this direction. So it is acting perpendicular to the area. No? So we call this as a normal stress. Now, if the area is applied, or if the force is applied parallel to the area, so if this is, let me erase. So kunwari lang meron tayong area dito and our force is applied along the area, so it's parallel. Then we have what we call as a shear stress, no? Okay, shear stress. Okay, so hindi siya masyadong important sa lesson today, but this distinction is is quite important when it comes to physical metallurgy kasi iba yung kumbaga um, kung interpretation ng two stresses na yun. And in fact, pagka nag MetE177 na, it requires na we have an understanding of how we translate or how we interpret these two types of stresses. No? Kasi we can have something like, for example, pag ganyan na stress. This is actually a mixed na stress. No? It has a normal component and it also has a shear component. Okay? So that's the two stresses, normal stress and shear stress. Tapos usually express siya in this form, no? The difference between your sigma and your S or your engineering versus your true is that magkaiba yung yung denominator natin. So when you have an engineering stress, usually when we do tensile test, no, using a UTM or a universal testing machine, usually ginagawa natin is meron siyang has two components lang, no? Meron siyang extensometer. So if this is your UTM, I don't know how to draw a UTM. Kunwari lang yan. Tapos yung dog bone sample natin. So I'm assuming you already know what a UTM is, no? So meron usually silang yung dog bone sample na nasa gitna. Tapos itong dog bone sample is held by two grips. Tapos yung grips is moving in the opposite direction. No? Sometimes pwede rin yung UTM kasi it can also do compression testing. No? So minsan may malaki kang two blocks dito. Tapos kunwari usually ginagawa siya sa mga concrete, yung mga ganun, yung mga ceramics. So usually yun yung kung saan importante ang isang compressive strength. No? So pag ganyan naman, pababa yung natin. Pero in any case, itong si UTM natin, it has two major components, no? Yung tinatawag na extensometer. Tapos meron din tinatawag na load cell, no? So the extensometer just measures yung incremental increase in the delta L, no? So kumbaga kung ano yung distance na to. So yun yung mini-measure ng extensometer. Tapos si load cell naman, ang mini-measure niya is the amount of force that is or the amount of load in newtons, kung ano yung kailangan para ma-pull or ma-push tong material that you are testing. Okay? So it matters because si load cell and extensometer do not actually measure stress and strain, no? And usually when we do, ang result kasi ng UTM test is a stress strain diagram, no? And to be accurate, it's an engineering stress strain diagram. Okay? So what it does is, kung tutuusin, ang minimeasure lang talaga ng load cell natin is forces in newtons, tapos extensometer, it's change in L, para ganyan. Yun yung minimeasure nila. So what happens is you end up with a graph, and this can be done by software, or minsan pwede din i-collect mo lang yung data, tapos afterwards mo na i-interpret using another software, no? Pero most modern UTMs, ito na yung ilalabas niyang results, no? But technically, ang nilalabas niya na results is actually just normal, is just actually the force, parang force versus delta L. Yun lang yung nilalabas niya. So what makes it a stress strain diagram is, if you have ever used the UTM before, and probably you'll use this in the future, no? Usually, pagka doon sa software, may in-input kang mga parameters. So may mga different parameters yan, no? May lalabas na parang pop-up dyan. Tapos may nilalagay kang parameters, and one of those parameters is actually yung initial area, yung A naught. So sinusulat mo lang dito yung initial area. So what the software does is, kung ano man yung force na nakukuha niya, i-divide lang niya by a constant A naught. Kaya siya engineering stress. And ano naman, strain, meron kang initial length na nilalagay. So over initial length, L naught. So kaya may strain ka na may papalabas na value. Pero technically, since you are just dividing by constant, no, this graph right here is just a force versus delta L. Yun yung actual changing values. Okay? So you can see by this, the way the UTM is handled, is that meron siyang, definitely may mga errors ka makukuha, no? Kasi as you, for example, if you are doing your testing, no? Kunwari ito yung sample mo. As you increase, nagkakaroon ng yung tinatawag na necking. We call this as necking. Necking is when your sample na tinetest mo, at the center or at the midway point, usually nagkakaroon tayo ng reduced na area, no? So hindi na siya yung same area doon sa initial value natin. So as you increase the and this is because of the law of constancy of volume, no? Kasi the volume should not change. If the volume is the same, kunwari V naught is equal to V final, then dapat volume is equal to area times length, no? Area naught times length naught. Tama? Tapos, ang volume final is area final L final. Parang ganyan. Tapos, we know that the final length, if this is a tensile strength, if the final length is increasing, no? Kasi hinahatak natin yung natin, sample natin eh. So, if it's increasing, then dapat we should get, if I rearrange it, LF over L naught. So, if this is increasing, dapat si final value should be decreasing. Tama? That makes sense, no? Kasi kung tumataas tong value na to relative to this value, then para ma-retain yung proportion nila, dapat ito bababa. Okay? So, it makes sense na nangyayari tong necking na to because of the constancy of volume. Okay? So, note, however, pagka meron kang engineering strain, we only input the initial area, no? So, consistent yung area na in-input natin. Hindi natin tinitake account necking na to. So, that's why hindi accurate yung engineering steps. Okay? So, we need to convert it into a true stress, no? And the way we convert it to a true stress is through this relationship, no? And actually, you can derive this relationship through etong relationship na to, no? So, from A naught, L naught equals AF, LF, pwede mo actually ma-solve siya. So, if engineering stress is, and I'll say sigma E So, maingay sa labas. Hindi ko alam kung naririnig niyo yan. Pero anyway, so sigma E is equal to F over A naught. Yung si ano naman, sigma T is equal to F over AI, where AI here is the instantaneous instantaneous area. No? So, ibig sabihin, as it goes along as it is being pulled, no, tinitake account mo yung incremental changes in the in the initial area due to this constancy of volume. No? Okay, so you can input it like this. So this is instantaneous volume. A naught L naught is equal to A instantaneous L instantaneous, and from here pwede mo na ma-derive to. So I won't show it anymore here, pero pwede nyo siyang ma-derive on your own. No? Okay, so that's engineering stress and how we can relate that. And usually you will end up with something that looks like this. No? And this is where your UTS is. This is the highest point. This is the ultimate tensile strength. And if you try to plot so you'll end up with something that looks like this. No? So parang this graph makes a lot more sense, no? Parang sinasabi dito that the stresses that the material is experiencing is always going upwards, no? Which makes sense, no? Kasi hindi naman nag-make sense so na parang meron kang maximum tapos biglang bababa yung requirement to cause the failure of the ano no of the material. So hindi nag-make sense na bumababa siya. Okay, common intuition will tell you na dapat if you want to further deform a material, dapat constantly tumataas dapat yung pressure, yung stress na ina-apply mo. So that's why itong true mas accurate siya. Okay? So we have that's our true value UTS, tas ito si ano, and usually the relationship, itong relationship na to is only valid up to UTS lang. Okay, anything past UTS hindi na valid yung relationship between the true stress and the engineering stress, as well as the true strain and engineering strain. Okay, so ito actually itong part na to, itong binroken ko, this is just an extrapolated value, no. Okay. Right. So, there dito naman sa ano sa anong tawag dito sa engineering strain, ganoon din, no. So, if we have let me erase this para may area ako. Sa engineering strain naman, if we have a sigma T, sigma E muna. Sigma E is just delta L over L naught. Tama? Or pwede rin isulat natin to as LF minus or Li instantaneous. So kung at whatever, kasi you can pick any instantaneous L, no, na instantaneous length, and you can get the strain value for that particular length. So you can call it instantaneous length minus initial over initial. Okay? Or itong L naught. Okay? Now, see, the way we calculate the true stress is through instead of using a change in L value over the original, ang ginagawa natin is kinukuha natin yung incremental changes doon sa or infinitesimal changes ng length natin as it is being expanded. No? So the way we express that is through this equation. No? So we have Ln is equal to Li over L naught. Okay? So that's how we express this, and that's why pagka inaano natin, we can actually just convert this now, no? Kasi if you look at it, this is just 1 plus, if you ano no, if i-rearrange natin to, this becomes Li over L naught minus 1. Tama? So this becomes 1 plus epsilon E is equal to, oh sorry, 1 plus epsilon E is equal to Li over L naught, and therefore you can substitute itong Li over L naught na to, substitute nyo dyan. So this value right here, which you end up with something like this. So kaya ganun yung relationship ni true stress and true strain, I mean, and true and engineering strain. Then from here, pwede mo nang i-relate din. Pwede mo nang gamitin dyan in conjunction with this, constancy of volume. Okay? So, in most of the equations, and that the reason why I started off with this discussion is because most of the equations that I'll be showing you will involve um, equations that need a particular na stress value, no? So some of the values require engineering stresses, some of the values require true stresses. So it is important that you can distinguish between the two of them. And ito yung sinasabi ko kanina na graph of the stress strain curve, or the engineering versus the true na curves, no? So the true curve, if you look at it, always increasing siya, no? Never at any point hindi siya bumababa. So this part A prime to B prime, this is actually an extrapolated value lang to, no? Extrapolated. Okay, it's extrapolated. And ito, yung relationship na sinabi natin kanina is only applicable to this part of the curve, no? Dito. So itong, we can only apply this part, no, dun sa um, doon sa plastic region. So plastic region hanggang UTS lang. Itong A. Here, this is the maximum load, no, or sometimes known as the UTS, no. So this is where the relationship applies. Relationship applies. Okay? Okay? So let's proceed with the first na parang important equation natin when we talk about true stresses and true strains, no, is the considers criterion, no. So ang sinasabi dito sa considers criterion is that this is a condition wherein the onset of necking is, or kung saan nagbibigin yung necking is where you have the point of maximum load. Okay? So for the engineering stress, it's this point right here, no. So itong point na to, where you have maximum load, this is where the start of necking occurs. So necking usually occurs in stages. So for example, the first na initiation of necking will involve parang numinipis itong area na to. After that, magkakaroon ka na ng, if further deformation is allowed, magkakaroon ka ng microvoids dito sa loob. And this microvoids right here, lalo pa niyang pinapahina yung material, no? And that's why anything past the UTS, anything past this part right here is no longer, kumbaga, accurate, no? Kaya nagbe-breakdown yung relationship na to kasi at this part, marami ng imperfections yung material natin. And eventually, from those microvoids, ninipis lalo pa yung yung area natin, and those microvoids will coalesce and develop into large voids, which will eventually lead to rupture at point B, no. Okay? So ang sabi ni Considier, yung criteria niya is that when the slope of the true strain diagram, d sigma t over d epsilon t is equal to the true stress sigma t, then necking should begin. Yun yung sinasabi niya. Okay? So this is kaya natin ma-derive to. This is from let me double check, no. Wait lang, nasaan yun? Wait lang, ba't nawawala? So the way we derive this, no, is um through the equation, or the parang if we want to take um the load equation. So let's represent load as dp, no, but we can also say DF siya. Sorry. So, or we can use F na lang para ano. Pero some textbooks use P, no, to indicate the load or the force. So let's just use F kasi since masanay kayo sa F, no. So we have the F is equal to 'di ba? Equal siya sa stress times area. Okay? So this is just a rearrangement of yung I don't know, sigma is equal to force over area. Okay? So we started off with F is equal to sigma times area, and so if we get uh the infinitesimal change of this force or the force requirement to further deform a material, then it's equal to d a, and this is kalimutan ko nung term dito in math, no, but I'm guessing na this is already discussed in one of the mathematics that you have took or you're currently taking. Sa amin kasi diniscuss to math 54 pa tawag namin doon. So hindi ko alam kung anong math siya ngayon. And Lawrence, tell me if this looks familiar, no? Maging sigma dA. So if you have something like x is equal to yz, dx is equal to y dz plus z dy. Does that
Yes, sir.
familiar naman, no?
Yes, sir.
Okay, nakalimutan ko. Anong math ba to sa inyo? Uh,
Math 20, 21.
21. Okay, so you're familiar with the concept, no? So that's how we get the infinitesimal change when it's a product, no? Product rule nga ba tawag dito? Baka tama yun, product rule siguro.
Yes, sir. Product rule. Product
Okay.
rule.
All right. So if we apply the product rule dito sa dito sa equation natin, F is equal to sigma A, then we end up with something that looks like this, no? dF A sigma D naught plus sigma dA. So how do we interpret this, no? This is actually a good equation, no? And this gives us an idea of how the parang the stress behavior is is developing as the material is being deformed. So this tells us that this is a if you look at this is this sigma. So this is actually parang strain. This is where strain hardening is occurring, no? Okay. So strain hardening siya kasi parang nag-i-increase siya. Kumbaga there is an increase in the sigma value. So parang if we look at the itong stress strain diagram natin, parang sinasabi natin that we are moving upwards this up dito sa natin sa stress strain curve natin. Okay, whether it's engineering stress or it's a true stress, there is a corresponding na sigma value, change in sigma value, no? And this makes sense, no, because 'di ba, from what we've learned in MetE176 is that strain hardening occurs when we deform a material. So when we deform a material, nangyayari is we introduce dislocations, and when we introduce dislocations, we could have a dislocation forest, and that dislocation forest will cause the hindrances to dislocation movement. Therefore, a material strain hardens. No? Okay, so so this makes a lot of sense. As we increase the force involved or the stresses involved, then we should be expecting a increase or a decrease in the in most cases increase, because it's strain hardening. And at the same time, if this is tensile in nature, no, we'll be dealing with tensile stresses lang muna dito, no, because in most cases metals are are weaker in the tensile direction as opposed to the compressive direction, and therefore mas relevant sa atin na aralin kung saan siya weak, no, para ma-address natin yung weakness na yun. Okay, so in most cases tensile lang parati yung example natin dito sa work hardening. Okay, so our material again is strain hardening as it is being pulled. So it makes sense na tumataas there is some change in the sigma value or the flow stress that is required. No? Okay. So at the same time that it is being strain hardened, meron din siyang change in the area, no? And we've already touched on this a few minutes ago. Sabi natin na as we introduce the load and we continuously extend the metal, no, parang hinahatak natin siya, because of the constancy of volume, it only makes sense na dapat yung area will be decreasing or magkakaroon tayo ng necking sa sa dito sa middle part, no? So therefore, tama lang na meron kang DA dito na term. So this DA right here is that as indicator of that. Okay? So ang sinasabi dito again is yung force required mo is actually a function of the strain hardening and as well as the change in the area. So tumataas siya dahil nagsistrain harden at the same time bumababa yung load bearing capacity ng material mo dahil lumiliit yung area, no? Kasi eto area na to, this is a constant multiplied by D naught, then kung tumataas tong load bearing capacity mo. Tama? Kasi this is actually a force as well, no? Kasi A times D naught is a force. So, or ito DF to. So, this is DF. Tapos, so meron siyang isang component na tumataas, meron din isang component na bumababa dun sa DF na yun. Okay? So, ang ano dito is, dito sa part naman na to, yung load bearing capacity ng material mo is lumilit kasi lumilit yung area na available sa inyo. Okay? So kung mas maliit yung area kasi tumataas yung stresses involved and therefore mas mahina yung material natin, no? Kasi for the same amount of force, so for example, if you have the same amount of force, tapos if you apply that to a large area, same force lang to, no? Versus something like this, same force, yung for this same amount of force, iba yung na-experience na stress dito versus sa stress dito. In fact, dito mas mataas yung stress value na na-experience niya. So meaning, yung load-bearing capacity nitong mas maliit na area is smaller, no? So that's why dito bumababa siya. So kumbaga may balance na nangyayari, no? Tumitigas yung material mo, nagiging stronger siya, pero at the same time nagiging weaker din siya dahil sa lumilit yung area. So what the considers criterion is saying is that we want to get the point at which we have maximum load, no? And if you have an equation like this, kung meron na tayong dF is equal to AD naught plus sigma dA, the way to get the local maximum, and you probably learned this in your math subjects as well, no? Is just to equate this at 0, no? So meaning, hinahanap mo lang yung slope kung saan 0. Kung kunwari, if you have a graph that looks like this, finding df or pwede rin dx or dy equals 0 is just saying na hinahanap mo yung point na kung saan flat siya. Okay? Because that is where usually the maximum lies, no? So pwede ganyan or pwede rin kung minimum, hinahanap mo dyan. Okay? So ito yung hinahanap natin. So we just equate this to 0, and if you equate this to 0 and you can do the math yourselves, no? You will end up with this equation right here. Okay? So the point of maximum load occurs when the ratio between the d sigma t and d sigma d sigma t and d epsilon t is equal to the true stress t that it is currently experiencing, no? Okay? Okay. So later papakita natin kung paano natin gagamitin yung equation to. So another observations that several materials scientists have already conducted, no, is that yung stress and dislocation density are intimately connected to each other, no? And the data supports that the assumption that the stress value is directly proportional to the square root of the dislocation density has been proven to be true, no? And we already also saw this kahit dun sa grain size. Yung grain sizes natin also are effectively dun sa Hall-Petch equation. Was that the Hall-Petch equation? Oro-One's equation, I mean. Nakalimutan ko ng equation. Anyway, merong equation doon na pinakita doon sa grain sizes, no, that shows that directly proportional siya sa square root ng grain size. Okay? And this is also true for I don't know for dislocation densities, and we usually express dislocation densities as um, with the Greek letter rho. And the equation can be expressed as a normal as a normal stress. This is a normal stress, or it can be expressed as a shear stress value. No? So itong shear stress, usually shear stress pwede namang sometimes it's just can also be referred to as sigma, no, pero in most cases when we say shear stress, yung tau yung ginagamit natin. So in MetE147, usually kapag may nakita kayong ganito, kung wari sigma x, sigma y, and sigma z, or sometimes sigma xx, sigma yy, sigma zz, this is usually referring to normal stresses. Tapos if you have sigma xy, sigma yz, and sigma ano bang kulang? YZ, XYYZ, and XZ. These are shear stresses. So this just means that ano no, ito nag-a-act siya along the primary X, Y, and Z directions. Tapos ito nag-a-act along a planar direction. No? So nasa XY plane nag-a-act yung isa nasa YZ plane, yung isa nasa XZ plane. Okay? So shear stresses. And you can use this or pwede rin, and in I think sa MetE147 we use both, no, pwedeng ito or pwedeng yung tau XY, tau YZ, and tau XZ. Okay? Sa ES nyo ata, tau yung mas madalas na ginagamit, no? They don't actually refer to this notation, and you're dealing with 2D 2D lang ata ang ng ES subjects natin. So usually hindi na umabot sa Z direction, no? So it's either sigma X or tau XY. Tapos may sigma Y and tau YX. And usually these two are equal, no, to balance out forces. So anyway, yung stress and dislocation density can be related to each other, no? And we can relate them in this equation right here. Such that yung ano natin, yung sigma and shear stresses are are directly proportional. Yung normal and shear stresses, I mean, are directly proportional to the square root of the dislocation density, no? Okay? Tapos itong ano na to, tau naught, and one interesting thing to note about this constant, itong tau naught and sigma naught, is they are interpolated na constants, no? If you look at it, interpolated siya or extrapolated siya papunta dito sa point where you have zero dislocation density, no? Pero this is kumbaga it's just a convenient constant, no? Hindi siya actually representative of any material property, because if you think about it, if you have zero dislocation density, that is saying that your material is a perfect crystal, no? Or is a perfect single crystal. Tama? Kasi kung wala kang dislocations, ibig sabihin, kumbaga yung lattice mo buo siya all throughout the material, which is very hard to do, no? And in fact, it requires a very intricate process to produce a single crystal. So that's not to say we can't produce single crystals. It just requires a very intricate process. No, one of the process we do is nakalimutan ko nung tawag doon, no, sa process na to, but actually parang meron kang spiral. What ends up happening is that you allow your crystal to grow along this parang itong spiral na to, and what happens is because it is growing in a spiral, meron kang preferential direction lang, so all other directions are kumbaga hindi energetically favorable. So since one particular direction lang yung favorable, ang mangyayari is only the crystals that are solidifying in this particular preferential direction, sila lang yung mag-solidify. And what ends up happening is you end up with a single crystal, no? Parang ganun. And you need to do this in a very slow rate, no? Nakalimutan ko ng tawag sa process, but maybe you can look this up on your own, no? Okay? So what was I saying? Sabi ko na ito again, yung itong ano na to, sigma naught na to, or tau naught, depending on if it's a shear stress value or a sigma stress value you're looking at. It's just a convenient constant, no? And it does not actually really exist. Kasi again, it's impossible to get zero dislocation. And if you do get zero dislocations, that is saying na single crystal siya. And single crystals actually have a very different na mechanical properties than your parang ano no, crystals with defects. So I think this was discussed in MetE176, no, yung the concept of single crystals. Okay, so that is the relationship of stress and dislocation density. And let me look if meron pa bang. Okay, kaya tayo dyan. So next is yung Taylor's relation, no? And Taylor's relation says that etong yung stress field daw that the dislocation introduces is varying by a factor of 1 over R. So pwede nating sabihin na si tau natin or the shear stress value is directly proportional or is approximately equal to mu, the shear stress modulus of the crystal lattice, multiplied by its Berger's vector. This B right here is the Berger's vector, and over the distance R, no? So this means na, and this makes sense, no? Kasi kung mas malayo ka sa dislocation, then dapat mas hindi ramdam yung stress na nai-introduce mo. So if you look at ano no, parang ganun. So kunwari meron kang crystal dito, and this is a half this is a half plane, no? So meron kang planes. Tapos we have a half plane, and therefore uh, meron tayong ano dito, edge dislocation dyan. So the further you are away from the dislocation, mas konti yung kumbaga, and if you look at something like kunwari nandito na, halos wala ka ng deformation sa lattice na na-experience, no? So again, yung stresses na na-introduce ng isang dislocation or isang grain boundary is because of the strains that it introduces dun sa crystal lattice natin. Okay? So it makes sense na as you go further away from the source of the dislocation, dapat smaller yung stress field na na-experience na. Okay? So if we try to i-combine natin yung mga constant, no, then we get tau is equal to K over R. Okay? And where R here is the distance from dislocation to dislocation. No? Okay? So if we have this K over R, if this is the distance from dislocation to dislocation, then let's just say na ano, no? Let's take an area, no? Mas madaling ma-imagine kasi kung ganyan siya. So let's just say na this is the dislocation. This is one dislocation located here. Na meron kang another dislocation here and another dislocation there. Kunwari ganyan yung distances nila. Or sige, mas parang pangit yung ano ko. Mas maganda kung ilalagay ko siya sa ano, no. Ulitin ko. So, kunwari meron tayong ano, no. Let's make it smaller, no. 3 by 3 na lang. Kunwari ganyan. So, if you have, for example, nandito yung dislocation mo. So, this is part of this parang, let's just call this an area, no? Tapos, yung next dislocation mo is nandito na. And yung next dislocation mo is nandito din. So, kumbaga, if I were to continue the lattice, meron din siyang, itong next dislocation na to is part of the next 3 by 3 na area. So, let's just imagine, no, meron tayong equally spaced na parang dislocations na ganito. So, you'll find out that itong distance na to, let's call this as let's call it 3 units na distance. No? Tapos ito, this is also 3 units na distance. You'll notice that if you have a scenario that looks like this, then the dislocation density is actually 1 per 9 unit area. Tama? 1 over 9. And therefore, si dislocation density natin, this is the dislocation density, no? This is rho is equal to 1 over 9. You'll notice na equal din siya sa 1 over r squared. Tama? Kasi r is the distance in between the dislocations. So, this is 3 units to the next dislocation, 3 units to the next dislocation. 1 over r squared siya, or 1 over 3 squared, which is 1 over r squared. And therefore, if we rearrange that, we can find out na si r is equal to square root 1 over square root of, oh sorry, 1 over square root of rho, or pwedeng since 1 over r to dito, pwedeng hindi na natin i-ano, no? I-square root na lang natin siya. So pwedeng mangyayari is we have, so if I take the square root of the both sides, no, from the left and the right, then I end up with rho square root of rho 1 or rho raised to the power of 1/2 is equal to 1 over r. Tama? And if I substitute this, I end up with this equation right here. So kung isa-substitute ko tong 1 over r rho, ito, I end up with this equation. No? So Taylor's relation says that yung shear stress na na-experience ng material is directly proportional to the square root of the dislocation density, which is the same observation na nakuha ni ng empirical data natin. Again, these are all empirical results, no? These are empirical results done by material scientists. Tapos they found out na if you plotted all the data that they got, ito yung nakuha nila, which is consistent with a mathematical approach by Taylor, no? Okay? Tapos yung last equation natin is the Oro-One's equation. So Oro-One's equation is saying that the final equation looks like this, no? Pero if you want to derive the Oro-One's equation, you have to begin with this one, no? So let's just say na meron tayong edge dislocation. Tapos it is moving across the slip plane, no? And hopefully you still remember how dislocations move. The dislocation can only move along a slip plane, no? So hindi siya pwedeng mag-move in any direction lang it pleases. It has to move along a slip plane. Okay? So if it moves along a slip plane, then we can say na ito, so for example, it has fully displaced from one location, yung dislocation mo pumunta siya fully displacing the crystal, then you will have a displacement that looks like this, no? Parang ganito. So you have a displacement equal to the Berger's vector B. Okay? Pero what if kunwari yung dislocation natin nasa gitna pa lang, or it's in between the starting point and the end point. Okay? So the displacement now will be a ratio, or kumbaga is only a proportion of the distance that the dislocation has traveled. Tama, no? It makes sense. So ang dislocation dito, displacement dito I mean, is equal to B multiplied by delta x over x. Tama? So for example, if it has only moved half, so kunwari lang, let's say na 100 units to, no? Itong buong dislocation na to. If it only has moved half or 50 units, then it makes sense na yung displacement dito, kasi hindi pa siya fully na displaced, di ba? So yung displacement dito will only be half, no? So kaya B times 50 over 100. So parang 0.5B lang dapat yung dislocation dito. If it moves, it has moved kunwari 3/4 of the way, so that's 75 units away, then it makes sense na dapat 0.75B yung dislocation dito. Or yung displacement, I mean. Tama? And if it has moved all the way up to dito na, kunwari yung dislocation natin umabot na sa dulo, then it has moved 100 over 100 units. So magiging 1B na lang, 1B siya, which is exactly yung case dito. Okay? So if that's the case, if it's moving only 1 over B pa lang siya, then we can actually calculate the strain na i-introduce natin. Okay? So the shear strain can be approximated by the, kumbaga, kung ano yung um, displacement niya over the z value, the height, kumbaga. So, if we know the height, then the shear strain is equal to, this is not the shear strain. No, we call this as this is the shear strain. Tama. This is the shear strain. So, if we do epsilon, ito ay lateral strain. Tapos shear strain is when the strain is applied parallel to the to the plane of action, where in this case it's the slip plane, no. So if that's the case, then we can relate the two quantities, no. So pwede nating sabihin na um delta B, we can say that the delta Y is equal to, kung full yung strain, no, equal lang to sa B over Z. Tama? Kung let's say Z value itong height ng crystal na to. Okay? So if it's the full value, then we can do something like that. Pero since we are looking at yung hindi fully displaced pa, no, then the change in the shear strain is just equal to delta gamma nga ba to? Alpha beta gamma, tama. Delta gamma is equal to the Berger's vector multiplied by delta x over x, tama, over z. Tama, no? That makes sense? Delta x over z. Kasi kumbaga, hindi pa full displacement. Only a proportion pa lang siya. Okay? And if we multiply it by the, let's just say, this is length L, no? So if we multiply it by L over L, so I'm just multiplying it by 1, then I get B delta x L over XLZ. And itong XLZ na to, this is kumbaga yung length niya, yung width niya, tsaka yung height. Tama? So this is actually just the volume, no? Tama? Over volume siya. Tapos ito, B, delta XL is actually the change in area. Tama? Kasi this is delta X here times the length is actually the area. I'm sorry, I'm not, hindi pala dito ang L, no? L should be, L is measured, siya yung kumbaga, pangit yung L na term na ginamit ko. Dapat width yung ginamit ko na term, no? Mas madali ma-imagine. Let's use W. So if I do W, sorry, X times W times Z. This is still the volume, no? Ito, volume. Tapos, sige, para mas, let me change the terms, no? Yung mas familiar tayo. Let's call this H para height siya. Tapos, let me redo din, no? So, ito yung H. Tapos yung, kumbaga, yung dimensions, if this were a crystal na ganyan. Let's make it 3D, no? Mari ganyan siya. Ayan yung H. Ang width is this dimension right here. Okay? Yan yung width natin. Okay? So sabi natin if full displacement B over Z siya, so kung a proportion of the displacement lang, then dapat B delta X over X over Z. Tama? Now, if we multiply this by width over width, so that's just multiplying by 1. So that shouldn't make a difference, no? XZW is equal to, this is X, no? So XZW is equal to the volume. B delta X is equal to B delta X times W is just equal to the area, no? Kumbaga, kung nandito siya, yun yung area na cover niya. Tama? Parang siya yung nandyan. So if it's traverses this one, then this is the overall area na na-cover na. So this is actually just B delta A. Okay? So from here, we know that yung wait lang. We know that this is ano no, ito kasing width na to, this is in a manner of speaking, no, this is the length of the dislocation. Tama? So if this is the length of the dislocation, then we can express the density. Density is equal to the number of dislocations multiplied by the width divided by the volume. Tama? Kasi dislocations can be measured either, there's two ways to measure dislocation, no? Something like this. So we can measure dislocation as kung naka-view siya as a point. If dislocations are viewed as a point, then we get the area. So kung ilang dislocations ang nagtatraverse sa area na to, so you can have something like this, no? Yan. So this is the number of dislocations over an area. So pwedeng number of intersections over area. That's one way to measure dislocation. Or instead of measuring the number of intersection, pwedeng, kunwari, if this is a mixed dislocation, no? Kunwari, ito yung mga dislocations na yan. Let's make it 3D. Yan yung dislocations natin. Pwede nating i-measure yung total length ng dislocation na to over the total volume. Which still gives you the same units, no? Kasi ito, this is parang unitless value over area. So parang 1 over, if you use SI units, then 1 over meters squared to ang units ng dislocation density. Das dito, if you measure the total na length, so that becomes meter over meter cube, which becomes 1 over meter squared. So this is actually the same, no? So we can measure it this way, or we can measure the entire volume, no? So in this particular case, measure natin entire volume. So our dislocation density becomes the number of dislocations multiplied by the width divided by the volume. Okay? So kung gusto natin malaman yung average na speed ng dislocation, we can say na okay. So saan tayo nag-end? So ito, this is the delta A, no? And actually pwede actually natin hindi na siya gawing delta A. Tama ba? Okay. I think pwede nang hindi natin gawing delta A ito. I-separate na lang natin siya. So we have delta X times W. Mas okay kung ganyan nakahiwalay siya. Okay? So we can say na ito for this particular case, B delta X times W over V. And itong W over V, this is just our raw, no? Raw value. So we can do raw B delta X. So raw, this is the length of the dislocation. So we are saying na in this particular case, sinasabi natin na one dislocation lang to. One dislocation moving in this direction. So this total length of this dislocation, and we are assuming parang straight lang siya na dislocation, no? An edge dislocation na siya. So we have the total length nito, which is just W over the total volume, is the dislocation density. So rho B delta X. Pero hindi pa siya yung dislocation density na we are all familiar with, no? Or hindi pa siya yung Orwan's equation na we are all familiar with. This is still delta X. So if we divide it by time, so kunwari, if we take the time for this dislocation, this dislocation is moving from this point to whatever delta x it ends up with. So if we divide it by time, then we do delta y over delta time. Then we can say na this is just the velocity, tama, of the dislocation. So we end up with the equation delta gamma over delta t is equal to rho b v, where v is the average velocity of the dislocation, b is the Berger's vector, tapos rho um, is the dislocation density. Etong delta gamma over delta t, we can actually, there is a specific term for this, no? So if this is the strain, if this is the average na shear strain, then if you take the average shear strain over a particular time, we call that as a strain rate, no? This is your strain rate. So it is represented by itong strain value tapos may dot sa taas, no? This means na that it is a rate, no? Now, it can be approximated na yung lateral strain na na-experience ng material is only half of the shear strain that it is experiencing, no? And this is and hindi ko na go into it, no, pero we call this as a Schmidt orientation factor, no? And the Schmidt orientation factor is approximately 1/2 for the for polycrystalline metals, no? So in this case, yung epsilon, and this is again, this is shear, no? Shear strain rate to. And this is your lateral strain rate, or sometimes just the tensile strain rate, no? Since again, most of the time we are dealing with lateral ba? Longitudinal strain rate pa, lateral ako ng lateral. Longitudinal strain rate, I should say. So longitudinal strain rate is just the tensile strain rate, no? Equal siya sa 1/2. Tama. So that's why we end up with yung famous na Orowan's equation. And MetE176, I think, discussed this already, no? That the sigma is equal to, or the strain rate epsilon, the epsilon dot is equal to 1/2 times the dislocation density multiplied by the Berger's vector multiplied by um, the dislocation velocity. Okay? So we'll do some calculations, no? And let's try to actually meron naman ng ano, no, mga footnotes dito, pero let's try to walk through the solutions of these examples right here. So meron daw tayong tensile test that was made on a specimen that had a cylindrical gauge section. So meaning yung sample natin is it's still a dog bone, no? Pero yung gauge niya is, or kumbaga cylindrical siya na dog bone. So you can imagine para siyang ganito, no? Tapos meron siyang cylindrical na cross-section area. So it has a cylindrical na gauge section with a diameter of 10 millimeters. So that's initial. And a length of 40 millimeters. So usually the length is measured from the part na, ano, baga merong, yung hindi kasama yung parang, ano man tawag dito? Basta yung fat part of the dog bone. No? So usually, dito mini-measure. And when you do yung mga extensometer din, hanggang dyan lang sila nagme-measure. No? Okay? So, after fracture, that is saying na after rupture, no? So, kumbaga kung stress strain diagram pa, after umabot na siya dito sa point na to, the total gauge section was found to be 50 millimeters. So, it had a increase in the area, 50 millimeters. No, sorry. The total gauge section was found to be 50 millimeters. So, it increased in the length. So it makes sense na if because of the constant in volume, if it increases in length, dapat nag-decrease siya ng area, no? And the area is said to is observed to be having a 90% reduction in area. Tapos the load at the fracture, which is measured in newtons kasi force to, the load at fracture is 100 newtons. So let's compute for yung specimen elongation, engineering fracture stress, the true fracture stress, ignoring the corrections for triaxiality at the neck. So meaning, let's ignore the fact that after the necking dapat hindi na dapat nag-apply yung ano, no, yung relationship. So that's what I mentioned earlier dito, no. Sabi natin Beyond the UTS, hindi na nag-apply dapat uh, yung relationship ng true stress versus true strain. Okay? So, saan tayo? Tapos, ang last natin i-compute is the true strain at the neck region at fracture. So, specimen allocation is fairly straightforward lang, no? Compute mo lang yung gauge length final minus yung gauge length initial, which gives you 10 cm. So, that's your delta L. Engineering fracture stress equals siya sa, is just the load at fracture, which is 1,000 newtons daw. Tapos, kung ano yung engineering, kasi engineering stress to, then therefore, we just use initial, no? So, hindi natin tinitake into account yung instantaneous stress. Okay? So, A naught lang siya. So, we have 1,000 newtons divided by pi r squared, which is r is, sabi kasi dito, it's a 10 millimeter yung initial niya. So, kaya diameter over 2. Usually, class pala, pag, ano no, when you say, sometimes hindi na minimension doon diameter, no? When you say a 10 millimeter pipe, kunwari, or a 10 millimeter rod, 10 millimeter section rod, ibig sabihin nun, ang 10 millimeter is the diameter, no? So, kunwari, kung if you have a rolling mill, kunwari, and they say a 2-meter rolling mill, they usually mean the diameter is 2 meters. So if no dimension is mentioned, usually it means that the mentioned diameter, especially for cylindrical na objects now, dimension is more often than not the diameter, not the radius. Okay? So that's why ito, although dito naman binanggit naman na no, diameter. So dito it's 10 over 2 gives you 5. 5 times 10 to the negative 3 meters kasi naka-millimeter yon. Squared is equal to itong Pascal, and we express this in megapascal. Usually pagka nag-express tayo ng stresses in megapascals tayo. Okay? So it's 12.73 at fracture. So ignoring the axiality, so hindi na tayo magko-correction. If you want to get the sigma true at the fracture, then we just get the instantaneous na stresses, no? And the instantaneous instantaneous area at the fracture, and the instantaneous area at the fracture is, sabi daw, nagkaroon daw tayo ng 90% reduction in area, no? So, kung 90% reduction in area, therefore 10% lang yung natira doon sa original. So, we just multiply the A naught by 0.1. Okay? So, if we do the math, we get 127.3, or parang times 10 ito, no? Okay? So, that's the true stress. Tapos, next is the true strain at the neck region at fracture. So, at fracture, ang sabi natin is yung true stresses is equal to yung instantaneous length over the original length, and that is ln ng ratio na to. So, nandito tayo sa ito, no? So, ganyan. So, we start with ln of L over L naught. Tapos, we know from the constancy of volume that yung pwede natin gamitin ito, no? So, dV is equal to 0 kasi since dV V is equal to L times A, then dV is equal to LdA plus AdL. Okay? So, from here, pwede natin siyang ma-compute, no? Although, hindi natin kailangan actually ito. Parang mas appropriate na gamitin na lang natin yung V naught is equal to instantaneous volume. So, we can have A naught, L naught is equal to A instantaneous, L instantaneous. And therefore, yung Li over L naught is equal to A naught over AI. Okay? So we get, pwede natin palitan to with this one. So that's why ito siya. Okay? So, kaya natin pinalitan siya kasi walang length kasi na binigay at fracture, no? Tama ba? Hindi, meron naman palang length at fracture. 50 millimeters. Okay. Sorry. Dalawa yung strain na pwede natin ma-measure pala, sorry. So we can measure it in terms of axial strain, tapos meron ding radial strain. Now, if we measure it in axial strain, we should get yung 50/40 yung gagamitin natin, no? So that's 50/40 kasi this is the final na na length, tapos ito yung initial length natin. Tapos dito naman meron tang area knot diyan, no. So it's the reduction in area. So pwede rin kasing i-express natin siya as a radial strain, no. And if you do the math, you get negative 2.303. So meaning it's negative kasi yung strain natin is such that it's making the area smaller than the original area. So papasok yung strain kumbaga. So sometimes sa sa ano tawag dito? Sa ES subjects ata, ang tawag dito is minsan ito is E-long or E-longitudinal, tas ito naman lateral. Lateral ba o latitude? Lateral ata. Okay. So, hindi ko alam kung familiar kayo sa ano na to. Pagka nag-compute tayo ng Poisson's ratio, di ba? Parang E-long over E-lat yung computation. No? So, this is the same thing, no? Itong axial strain and radial strain. E-long and E-lat. Okay? So, let's do one more examples tapos we can end the session, no? And I'll leave it sa inyo na para i-solve yung kasi meron naman siyang mga footnotes naman. So probably you can look at this on your own. So ano ba magandang example? Should we go engineering? Check ko lang class kung ano yung pinaka magandang tingnan natin. This is what's equation. I think maganda to. Itong Holomon equation. No problem, no? So, Holomon equation is sometimes known as the power law, no? Minsan tinatawag itong power law. And this is the governing equation for most metals that are experiencing plastic deformation. Okay? So anything past, kung dito sa first na part, no, ang relationship nila is Hooke's law, no? Tama? Where we have yung sigma is equal to K epsilon. And kalimutan ko kung let's just search Hooke's law. No? Ano bang letter ginagamit ni Hooke's law? Hooke's law uses Hooke's law Hooke's law uses E, no? Capital E, which is the modulus of elasticity. Okay. So, in the elastic region, this is the modulus, and we call this as the modulus of elasticity or Hooke's modulus. Ito, kasi linear pa lang in the elastic region, we have a linear na trend. And this is the governing na relationship. But once you go past the yield strength or yield point, then you now experience a different na curve, no? And this is governed primarily by the power law and also known as the Holomon's equation. Okay, so the equation goes something like this. Sigma T is equal to K epsilon T raised to the power of M, where K and M are material constants. Tapos we express all the values in terms of its true stresses and true strains. Okay. So if we assume that K is equal to 750 megapascals and M is equal to 0.6, and we know that the true stress at the point of maximum load is 552, then what is the true strain at the maximum load? Now let's compare the M and sigma T at the maximum load. Okay, so let's start. So let's substitute first the given values into the Holomon's equation. So we have 552. Input natin siya sa sigma T side. Tapos yung 750, this is the K. Tapos 0.6 is the material constant M. Sometimes we call this as the strain hardening exponent or SHE. Okay. So sigma T is equal to 0.59997, which is approximately equal to 0.6. No? So we can observe that at M, at the maximum load, M is equal to sigma T. Okay? So how can we prove this, no? Dito? And we can prove that at any given point or at the maximum load, this will always hold true, no? So let's take into consideration yung considered criterion na diniscuss natin. Sabi natin sa yung considered criterion is that yung D sigma T over D sigma E at the point of necking, which is the maximum at the point, which is also the point of maximum load, no, is equal to sigma T. Tama? That is your considered criterion. Okay. So we start off with getting the derivative of both sides, no? So we derive. So that's D sigma T is equal to M K epsilon M minus 1 multiplied by D sigma T. Okay? So ito, pag dinerive natin to, we end up with this one. So if we rearrange, we end up with D sigma T over D epsilon T is equal to MK epsilon T raised to the power of M minus 1. So nilipat lang yung itong value na to sa other side. Okay? Now let's consider, now we input considers criterion which states that, again, for necking or for the point of maximum load, equal lang tong value na to, itong ratio na to the true stress that it is experiencing at that particular point. So if we substitute, we end up with sigma T is equal to MK epsilon M minus 1 over T. Now, if we resubstitute yung Holloman's equation on the left-hand side, we know that the sigma T is sa Holloman's equation is equal to ito, K epsilon M to the T. Then if we re-input that, we get this equation. Tapos cancel out all the unnecessary terms. So K cancels out to sigma M. Ito kung so magiging sigma raised to the power of mt over sigma raised to the power of m minus 1 t. This just becomes, if we, kung i-simplify natin to magiging m minus 1. Tama? E raised to t raised to the power of m minus 1, which gives us plus 1. Okay, so that's why sa left-hand side, it becomes sigma t is equal to m. So, we can prove that from considered criteria, no, na at maximum load, it is observed that yung M value will be equal to the strain. So kung ano yung strain hardening coefficient niya, equal lang din doon sa epsilon, yung true strain at that maximum load. Okay? So yun lang muna siguro. And I think ito kaya na nang siguro ma-solve on your own. Since we have no more time na, no, we can end the discussion here, or pwede naman I'll continue discussing siguro. Sige, i-continue ko na lang i-discuss 2 more problems. Tapos if you have if you need to go ahead, yung nandito ngayon, shout out pala kay Joanna and Lawrence na pumasok ngayon, no? So if you have to go, Joanna and Lawrence, then you can
Yes,
just
sir.
you can just exit the session, no? Pero nire-record ko naman siya, so pwede nyo na lang i-view later on. Okay? So I'll just discuss some of the maybe 2 more problems dito. Right? Sige. So continue tayo sa example 4. So the table shows the set of data for the variation of the flow stress with the square root of the dislocation density for titanium specimen. So, kumbaga given yung this is our experimental data, no? So, meron tayong nakuwang from a tensile test, yung yung stress na kailangan para i-deform siya given a particular na dislocation density. And already ito sa column na to naka raised to the power of 1/2 na siya, no, or naka square root na siya. Okay? And strain rate is given. And based from these results, let's compute the increase in the dislocation density that would correspond to an increase in the flow stress from 80 to 95. So flow stress is an important concept pala, class, no? Although this will be mostly used sa MetE177, pero as early as now, maybe I can explain this right now, no? So if you have, for example, itong um, in this particular case, no, kunwari, meron tayong material, nag-undergo siya ng ng changes, for example, yan. So if I were to do a tensile test, tapos i-release ko siya, tapos up to this point, ito dapat yung kailangan kong stress, no? So nandyan siya. Now, what happens if I release this stress, tapos I expose the same material to another tensile stress? So the tendency is, or the material, if I expose it to another test, it will still follow the Hooke's law, no? Sa dito sa plastic region, Hooke's law pa rin ipa-follow niya. Same line yung ipa-follow niya. But this time, magbabago actually yung yield strength niya. Actually, magi-yield siya up to the point kung saan siya tumigil the last time around. So magiging ganito na siya because of strain hardening effects. Parang ganyan. Now, if I did that again, kunwari, tumigil ako, let me use another color, no? Kunwari lang, tumigil ako dito, the same observations will be made, no? Follow pa rin siya ng Hooke's law, dire-diretso pa rin siya, pero hindi siya titigil dito. Titigil naman siya dito kung saan siya last na experience yung flow. So in that sense, and obviously magbabago itong rupture point, no, kasi may strain hardening effects na eh. So magkakaroon ng brittleness. Pero anyway, ang point dito is that actually depending on how much strain hardening is introduced on the material, nagbabago yung parang apparent yield point niya. And we call that as a flow stress. So kaya siya tinawag na flow stress because it is the minimum threshold of stress needed to continually plastically deform your material, or in a way continually make the material the metal atoms flow. Kumbaga kasi when we are plastically deforming, essentially parang nagpo-flow kasi yung material natin, no. So if you want to continue that quote unquote flow, then you need to overcome the threshold, no. So ang nangyayari is at any given point, if you know the amount of stress that you are or the amount of strain that it has experienced, actually kaya mo malaman kung ano yung particular flow stress na at that strain na value, no, alam mo kung ano yung flow stress na kailangan, no. Okay, so this is your flow stress. So that's the concept of flow stress. Okay, so dito ang tinatanong is ano daw yung corresponding flow stress, increase in flow stress, ano yung corresponding dislocation density if we were to increase the flow stress from 80 to 95 MPa. So to solve that, gagamit tayo ng linear regression, no? So we are already given 4 points, no? So these are 4 points and we can use this equation. Ito yung empirical equation na na-observe natin kanina. And from here, you can use either pwedeng Excel, pwedeng can use Excel, pwede ring calculators. I think most calculators, no, have a built-in parang linear regression na model where you can input different xy points, no, tapos siya na yung and essentially kasi linear equation lang to. This is a y equals m sorry, y equals mx plus b equation, no, where x is your square root, kumbaga ito yung x column natin, tapos ito yung y column natin. So if we have the x and y columns, pwede natin siyang makuha na tong b and m values, no. Okay? So if we get the M and B values, then the y-intercept is just the sigma naught, and the K value is equal to the slope. Okay, so we arrive at this equation right here. Now, solving for the dislocation density at 80 megapascals, then we have uh, we can input a particular y, no, and this will be equal to 269.51 dislocations. This is the dislocation density for the approximate na dislocation density associated with a um, flow stress of 80 megapascals. Okay? Tapos at 95 naman, we can also compute that, no? I-input lang natin sa equation because we already know the constants sigma naught and the K. So kaya natin i-input din siya. Solve natin yung dislocation density. So after we know the dislocation density, kaya na natin makompute yung delta rho niya, which is the increase in the dislocation density. So from 200, para ma-achieve mo yung, so interpretation ng sagot na to is that in order for you to achieve an increase in flow stress from 85 to 90, kailangan mag-jump yung dislocation density mo from 269 to 483. Okay? And that translates to a change of 213 dislocation, a dislocation density change of 213. Okay? So, sample 4, and I can do one last example na lang, no? Itong si example number 5. So for some metal alloy, meron daw tayong true stress of 345 megapascals that produces a plastic true strain of 0.02. How much will a specimen of the same material elongate when a true stress of 415 megapascals is applied if the original length is 500 millimeters? So let's assume a value of 0.22 for the strain hardening exponent n, no? Which is the same exponent yung m kanina, no, doon sa Coulomb equation. So sometimes they use m, sometimes n. So they mean the same thing, no? Okay? So first, ang gagawin natin is input muna natin yung we set up the Holloman's equation. No? So again, Holloman's equation, sometimes known as the power law, is sigma T is equal to K multiplied by epsilon T raised to the power of N, where again, yung subscript T indicates that this is the true values yung kukunin natin. So given naman is true values, no? A true stress of 345 megapascals, we put that in the left-hand side. We know the strain at that particular na true stress value is associated with a true strain value of 0.02. So 0.02 dito. And therefore, makukuha na natin si K. So our K ends up as 816 megapascals. With K already known, we can now solve for the plastic strain at 415 megapascals. No? So we already know K. Input natin siya dito. So if I were to write the equation, sigma is equal to K multiplied by epsilon raised to the power of N. Okay? So this is known. Sigma is known. K is known. N is known. Pwede natin mahanap si epsilon T. So if you do the math, then we end up with 0.0463. But take note, this is still true strain, no? This is true strain. So from this true strain value, pwede natin makuha yung initial, this is true strain. So kailangan kasi natin mahanap itong Li so that we can compute for delta L, no? So we know the true strain is 0.0463, and if we equate it with the true strain equation, that is equal to Ln times yung instantaneous L over the original length, no? L naught. Okay? So we have Li is equal to 500 because this is our, if you rearrange this, no, this becomes L naught is equal to Li, no, sorry. Let's backtrack. Magiging Li over L naught is equal to E raised to the power of 0.0463. Okay? So if we rearrange, lipat natin yung L naught dun sa kabilang side, we end up with this one. Okay? So this gives us an Li of 523.7. So kumbaga sa ano pa, alam natin kung gaano kalayo yung Li na tinravel natin to achieve itong condition na to na 415. Okay? So this is the instantaneous length. Okay? So if you want to get the elongation L, then you just itong instantaneous length natin, if you deduct the original na length, L naught 500, then you get 23.7 millimeters. Okay? Sorry. Baka ma-confuse kayo pala dito. This is may certain amount of strain na dito. Sorry. Certain amount of strain at Li. Okay, pwede siguro mag-end na tayo doon, no? And ito, marami namang footnotes dito. I think you can look into example 6 on your own, and ano yung skinip ko, example 2 ata, skinip ko din. You can look at example 2 on your own, you know, Aura 1's equation. Okay, so that's all for today. So thank you. Umalis na sila, pero thank you for coming in today, si Lawrence and Joanna, no? And for those na hindi nakasama ngayon, pwede nyo namang i-view yung recordings later on. I'll be uploading it soon. Okay? So see you next week siguro.